So if you see this particular data set, what is it actually you understand from this? See here, I have two types of variable you have. So this indicates the variable view. This is actually a SPSS, ideal SPSS. So this gives you the description of these things here. So age in years is these are the variables and their type, their numeric, etc. are non-numeric, etc. So that is you have all these things as a pattern. So these many that as a top thing. That is numeric, comma, dot, sanctification, value, custom analysis. So this is actually a tool. So tool for analyzing the data, raw data. That's all. So the width and the decimal places, etc. You can also have this here. Okay, this is actually a secondary aspect. The primary aspect is that if you just see this here data, so you find that these are cases. This is age. This is gender, faculty, status, stones, pounds, kilos, feet, meters, and some data is missing. So when you have this thing, so what statistically analysis I can do? That is number one. Number two is that here, what is actually this data type? So do you know that here what data type, not computer aspects of data type, data structures. I'm not talking about data structures or data types of computer aspect of data type. I am talking in terms of data analysis, data type. Do you all know or no? So what is the actually here? Data are of say categorical data. Right. So then measurement data. So these are the two types you find it. You find it only two types. So that is one is categorical data and the other one is measurement data. Once again, this data is being divided into nominal, ordinal. So in ordinal also you have binary and more than binary, that is greater than binary, so that is ternary, etc. So this is what actually you have. So what is nominal? Like if you just see this here in this, so this is actually a nominal scale. Gender is actually a nominal scale. One is male, two is female. Right? So nominal scale. So if I just take it that faculty also, this is into a nominal scale. Right? So if you just see the status, so status means what actually whether they belong to the undergrad, postgrad, or a medical graduate, or a science graduate, or etc. So these are the various categories you have. That's what actually we specify under coding. If you just go to the variable view and see this here, see here, we have coded the data as what? One as male and two is as female. So this is the most essential aspect of data analysis. Right? So why this is I call it as so much of stress I am giving for this, because if I know the data type properly, I can as well use a proper statistical analysis. Right? One, I start with a negativity. Like here, if I just take it as male and female, so my data says that here 1 and 2, 1 and 2. So I can as well, if I want it, I can as well calculate. One thing is, I say frequencies. So I say gender. Right? So then I can as well have the charge. Right? So I can as well get the table here. So there are 334 valid cases are there. And then I just get males are 203 and females are 131. Then I have the corresponding visualization of the data on the same frequencies, and that is that turns out to be male is this, and then this is what actually you have. Right? So what does this give you? This gives you the idea that the data collected on this particular nominal variable, it indicates that here it is actually a male-dominated survey because there are more number of males than the females. Right. So this is what actually I can as well understand from this particular case here. So the next thing is that here, if I just take this data and then if I just do the descriptive statistics, so that is so I just see here. So this is my gender in 34 cases. 2 minus 1 is 1, minimum is 1, maximum is 2, mean is 1.39, standard deviation is 0.489, variance is 0.239. So the average of 1 and 2 turns out to be 1 point. How much? It is 1.39. So what do you mean by this? Can I have an average value for a male and a female average for a nominal variable? Will it be a meaningful distance?
They can be half in half in.
No is correct, but the explanation is wrong. Yeah, that's it. So 1.39 is cannot be taken into consideration as a sense here. So a male or a female cannot have a 1.39 as the average value. Right? So it should be a clear cut. So that means what actually? Nominal variable, you should never use averages. Right? So what else you can do? What else you can do? So then nominal. Suppose if I have the data, right? So I have shown this particular data here. Okay? So here most of them are nominal variables. Okay? And what is this variable? Age. Age is nominal. Ordinal. Right. So yes, so this is your age variable is continuous data. Right. So this is actually continuous data. It is actually a measurement data. In that. Right. So nominal variable is not fit for descriptive statistics except median and mean. You know what is median? Median is middle value of the data points which you have. So where the data is in nominal nature. Then mode. Mode is most frequently occurring value. Right? So here nominal variable is fit for what actually? Mode, median. Then you have what is known as the chi-square. The chi-square test, which is used for testing the theory of attributes. So that is, I say that here my attribute is gender, and also my attribute is faculty. Right. So that is the thing which we want to study. So definitely, whenever you talk about categorical data, you just only talk about nominal variable and ordinal variable. So here you don't have an ordinal variable. How does ordinal variable looks? Right. So, yeah. So, what is actually ordinal variable? So, ordinal variable is again actually I say that here, so if I pose a question to all of you that do you like the president's economic policy? The alternatives are what actually there could be some alternatives. What is that? Like, dislike, neutral. So there are three categories. So when you have these three categories, like has got a highest preference, right? And then neutral is next to highest, dislike is next to the neutral. So that is least priority is dislike, highest priority is for liking, neutral is in between. So that means I say that here my data has I just coded like as 3, neutral as 2, and dislike is 1. So this type of data is called as what actually ordinal data. So order preference has to be maintained. So that type of a situation is called as what actually ordinal data. So this has got the highest priority. Next is neutral. The dislike has got this. But sometimes if you don't know these preferences of ordinal data, suppose if I just give a like as 1, 2, and 3. So suppose if I just give it. So ordinal data you can also calculate the descriptive statistics. Right? Why? Because I want to know that here what is the liking percentage, what is the disliking percentage, what is the neutral percentage, the average value. Suppose if I just give this thing, and then if most of the people have answered like, and then this will be around 1 point, less than or equal to 1 average value. Right? So then definitely this is actually, see that your liking has got a least priority. That's what actually happens. So that's the reason you have to first identify the data type. If we say data of this nature you are collecting it, so this one has to be given as the highest priority. The positivity is being given as a highest priority, and the least this thing is being given a least priority. So that is this type. So this type of a situation has to be taken into consideration under the context of categorical data. So only these two types of things you have. And the statistical test which you do is that one is nominal. The statistical test for nominal data is median, mode, chi-square. For ordinal, you can do any statistical test, t-test, f-test, or whatever you want to do. But only because you have to identify that this is like you are dealing with the ordinal. So that is what actually. Suppose if it is the data is multivariate. What is multivariate? Suppose if I just take one individual, his height, weight, BMI, body mass index, and as well as some other measurements as his clinical data. If I just take it here, his blood pressure level, cholesterol level, etc. These are all measurement data. When you take it measurement data, so on each individual, some 10 observations are just taken. So 10 students, 10 students into 10 observations, there is around 100 observations you have. Right? Whole data. So this data is dealt with what actually it is dealt with multivariate aspect. Right? So in most of the data sciences and big data analytics, high dimensional data analytics. So there you don't find only a single variable. It will be multiple variables. When you have multiple variables, definitely the analytics has to be done for a multiple variables, not very single as we have seen. So here if you just see the data which I have shown, age is only one continuous variable. The rest of the things are nominal variables. So when you have that type of data, so the corresponding measurement data has to be evaluated with a multivariate test. So those are actually called as advanced modeling instruments. So that is what actually the data type. Yeah, just glance through this here. So as I told you, the categorical data and measurement data. So this is whenever your objects being studied are grouped into categories based on some qualitative trait, the resulting data clearly labels are categories. So that is what actually is called as categorical data. So these are the examples of categorical data where plotting brown, red, and black, then opinion of students picked up, then critical and happy, scope status is better. So this is what actually you have. So once again, the categorical data is being divided into as I told you, the nominal and ordinal. Right? So that's what actually nominal data can be binary or not binary. Ordinal data can also be a binary or not binary. So ordinal data is no order. Differences are not there. So ordering has no preferences. Right? So next is here. So examples of this is plotting, plot, red, black, race, location, category. Right? Suppose if I just take it 10,000 databases, right? I want to pick up a particular variable. So that variable should, if you just take it, that variable to be a continuous variable or a discrete variable. So that you have to justify yourself and then select that type of a variable and do the proper analysis. You may not be really interested in knowing the real analytics of that particular variable, but even if you want to have a frequency cannot be drawn for a income level. Incomes are different income levels will be there. Right? Suppose if I say that you are cadre wise, I want to compare cadre. How many cadres I have my employees? So how many managerial level? How many are there? So then definitely this is actually a categorical data. You can as well do for these 10,000 data points. I can as well get a frequency table in one particular code. Right? So more than that, I may not do any analytics for this particular data. Suppose if I want to know the here whether my experience and as well as cadre, if I want to know that here, I cannot. How do I do it? How do I analyze this? Cadre and as well as experience. So in this cadre, how many are having this many experience? So that means actually, suppose if I have 10 categories, I have 10 rows. Right? 10 rows will be, I have 10 rows. Then I have how many years of experience? 1 year, 2 year, 3 year, 10 years of experience. I have 10 columns. So then I just get whatever, so cadre 1 to 1 year experience. So not one person, there could be out of 10,000, there could be some 200, 300 people will be there. So now the number which I get it here, 200 or 300, what is that actually? It is, though it is looking like a number, but this is actually a frequency. Frequency is not actually a continuous data. What is the distinction between a frequency and a continuous age or income? What is the distinction? So this is what actually one should be very clear. So the distinction between continuous variable and as well as discrete variable. What is the distinction? Continuous value is that's what actually. So this is 0 to 1 is continuous. 0 to 100 is also continuous. Yeah, this is specific. This is also specific. Yeah, age I have taken the 50. So all the 50 students age I have taken. So will it be a continuous or a discrete? Why discrete? Yeah, that's what actually I'm telling you. Suppose if I say that here age in this particular class itself, if I ask all the age groups here, or actual age if I just take it. So according to your mistake, this is discrete. Then you said discrete. Yes, someone said discrete. Right? So how do you identify the data given to you is actually a discrete data or a continuous data?
Values are real.
which are spelling number. That is repetition, right? So you going to say that your age groups repeat, then you say that your is continuous, otherwise it is discrete. But he said correctly. Gaps. Gaps. So when you have gap, definitely the data collected is actually a discrete data. When you don't have gap, it is actually a continuous. So I'll tell you a simple example. All of us have smartphones, right? All of us have. So during this particular 1 hour, you just see that here, how many of us got telephone calls on their 1 hour? Continuously are getting any, no one will get continuous. So the data which you collect on this type of a situation is never continuous. It is discrete. The number of air accidents taken is not continuous. The number of suicides taken during the 10 years is not continuous. Right? So here continuity means what actually? There should not be any gap. It should occur continuously. Then only you say that it is a continuous data. So continuous data is measurement data. Discrete data is categorical.
For example, any enumerated type is a
Which one?
Enumerated data type is a discrete, like a Monday, Tuesday, Wednesday, Thursday, Friday, Saturday.
Yeah.
But at the same time, the time is not a discrete, it's a continuous.
Yes, that's right.
Time is a continuous, but the day, Monday, Tuesday.
Yeah. So there is a gap between this. Happening also is a gap. Yeah, that's right. So that distinction has to be very innovative. Then only analysis can be done. So then you must be wondering what is so great in identifying continuous data or discrete data. Yes. So that continuous data. Your daily temperatures is a continuous data. Your income levels are continuous. Actual income is continuous data. Suppose if I just categorize the income level, it is not continuous. 1, 2, 3, 4, 5. So this, see, all your Oracle databases have this. See, you have actual age. You can see here always the danger is most of the people, researchers or even analysts, they think that their categorization is pretty easy. But it really doesn't convey any message to you. Why? You are suppressing the continuous data into categories data. Your hands are tied off. Why? You can only use a chi-square test. Suppose if it is continuous, I can do umpteen number of statistical tests. So actual data is really actually more useful. The continuous data has got a lot of potential to do a lot of pattern evaluations. So that is what actually our interest. So that interest should not be stopped. Whenever you are collecting data, whenever you are seeing data. So these are the most essential aspects. Though they look very silly and simple, but these are the crucial things. They are the backbone for statistical analysis. So as I told you just now, the thing is I started with the negative note that average age is 1.39. So only few people have understood that here, yes, it is long. But I have seen umpteen number of research papers for which these categorical data they have used the mean, which is wrong. Papers are also published. That's a different issue. Publishing is a different issue. But I say that here it is not really giving you a good indication. So that means actually the person who is using it, he doesn't know. Because so already the donkey is with us. So if you just say that the donkey to work properly, it will work properly. Otherwise, it gives you all wrong results. Right? So that is what actually people are doing. So that's exactly is the thing you have. So a type of categorical data in which order is important is this. Fresh is I say fresh is 1, sophomore 1 is 2, junior is senior, super senior. So that is what we are doing. So I cannot take this as the highest value and that as the least value because I want to give more priority to super senior than the fresh. So that is that understanding has to be clear cut understanding should be taken by the analyst, and then as per that particular list, the coding is done. Okay? So, opinion of students about rights and etc. So, a type of categorical data which have only two categories, binary data can either be a normal or a odd. So, that's smoker, non-smoker, closing caption, lower class one, upper class one, binary data. So, here, lower class one has least priority, upper class one has what? Highest priority. So, this is ordinal binary. Smoker, non-smoker also. Ordinal binary. So, this is present absent, also ordinal binary. So, that distinction we will going to do. So then next is quantitative data. So these are the quantitative examples. So discrete and continuous. So I said that gap is discrete, continuous is continuous finite. So this is what you will be talking about the gaps. So really, whenever you have a gap in between two observations, the gap could be here 0.5, the gap could be 0.75 here, or it could be one jump. So that type of data is actually called as a discrete. Continuous is no gap at all. So that distinction is given. So generally discrete data counts as a frequencies, tables. So those are the discrete data. So continuous data directly the measurements. The measurement of cholesterol level, height, age, and so these are all measurements. So this is ultimate is this. So the type of data collected in a study will determine the type of statistical analysis. So this is the most essential aspect of data analysis. If you don't know this data type, then you will be bound to apply a wrong statistical test as I just for sure with the simple listing as applying a average value for it. So this is what actually is that here. So ultimately, this is the data analysis is these 4 points. So the valid data analysis starts with the solid planning of a study. The valid data analysis must have a valid set of data. The appropriate statistical procedure are key to data analysis. So the analysis needs results. So these are the various aspects of data. If you have these 4 together, then you definitely do the data analytics. Okay, coming back to the same this one. Yeah. So here, when I do the data aspect, so here, any data science guy will do this. He has to know this here. Statistical inference. So it deals with the 2 categories. One is estimation. The other one is estimation. By the way, how many of you know the statistical background? Yeah. Anyone? No. Only no. How about this? No one. So estimation and testing. What is estimation? Suppose if I just take it, so this is actually, you consider this to be n equals to 5, which is actually indicates a population. So from here, I draw a sample of size n equals to 2. So that is 1, 2, so without replacement. 1, 2, 1, 3, 1, 4, 1, 5, 2, 4, 5, 3, 4, 3, 5, then 4, 5. So I have 1, 2, 3, 4, 5, 6, 7, 10 samples. So how do I get it? So 5, 6, so this is 5 samples, 5 samples again, 5 500. So this equals to 10 samples without replacement. Without replacement, If 1, 2 comes, 2, 1 should come. So 10 samples. So with this, I can as well. So this is my population. I can as well draw the average value. So I say x bar or mu equals to. Right? So this is called as what actually? This is my estimated mean. Right? So this is my estimated mean. Right? So this is what actually this is my sample. So all these samples are coming from this particular parent population. So that means there is no bias. Every observation which is repeated here or drawn here are belonging to this particular population. Right? Am I correct? So now what is this actually I do? So this is one sample. So for this sample I just calculate the mean. So this I call it as x bar. All population estimates are always uppercase. All sample estimates are lowercase. So the lowercase means actually x bar. So x bar by 2, so this equals to 1.5. So similarly, I just calculate this 1 plus 3 by 2. So this is 2. So this is x2 bar. This is x1 bar. So like that, I just calculate. So this is called as estimation. Right? So when I just calculate these means for this particular problem, I get the estimates. So now what is that actually my interest is? My interest is that here whether these estimated value is it acceptable or not. So people say that your statistics is damn nice, so you cannot rely on that. Right? So suppose if I don't do this, I will also support that here yes these could be lives. But always all statistical tests which you do has to be tested by the testing procedure. So what is the testing procedure? The testing procedure is nothing but by framing a null hypothesis. A null hypothesis. So here the data which you collect, or data which you see, or data which you handle will always follow one particular distribution, and that particular distribution is called as what actually is called as a normal distribution. It's called as a normal distribution. So a normal distribution is nothing but this is also known as a Gaussian distribution. Right? So this is your normal distribution, which is a bell-shaped curve. Right? So the area under this particular curve is called as AUC. Area under curve is actually it is how much total area under curve is 99.7. So this is the ordinate value is -3 plus 3. Right? So what is my null hypothesis coming back to this? So I say that here whatever I want to test it, like for example, you just take this. So if you see this here, I'm just comparing gender as one attribute. Then faculty of attendee is another attribute. Right? So now I want to say that here whether the male female who have registered under this particular 3 types Is it differing significantly or not? Differing significantly means what actually, is there any difference? If I see these figures 53, 97, 45, right? So this is not equal to this is not equal to this. And the total is 195, the total of males in these three categories is 195, and the females in these three categories is 124. Right? So there is a difference, 195 and 124. Right? Is this difference? So I have estimated that this is what actually you have. Now I have to test it as per the statistical inference aspect. So I have to test it means what actually I have tested that what actually this is an attribute. So association of attributes. For association of attributes, that is, you want to build up a relationship that the male female who have registered under that particular college, whether these three are differing significantly or not. Yeah. Yeah. You want that? See here, what is this? Suppose if you say that here, arts, science, medicine. Right? So I'll just take only two things. It is simple. Yeah. So what is arts? Observed. Observed is 53. Science? 97. Then this is me. 27 and 55. So this is my observed. Right? This is my observed. So what is this here? 7 plus 3, 10. 51, 50. So this is 12, 6, 1, 8. The total is 2, 13, 13. So here 2, 150. So here it is 10, 8. So this is my n. Right. So now you want, so this is my observed. So now I want to find out the expected value of 52. How we can get to the parts and divided by 150 into 80 divided by 250. So this is no percentage. The figure which you get it will be the observed. So for that, so this will be the observed. This is observed. This is the expected. Right. So similarly for this, expected value of 97. 97 is 150 into 152 divided by 230. Right. This no total, this column divided by this. Right. You get it. Similarly, expected at 27. That is how you just get the expected. So now what is this actually? This is actually a tester, chi-square tester, deals with what? Sum of I equals to 1 to n, OI minus EI square by EI. OI minus EI square by EI. So that value, I just calculate 4.58. So how I got this 2 degrees of freedom? There are 1, 2, 3 columns and 3 columns, 2 rows. 2 minus 1 is 1, 3 minus 1 is 2. 2 into 1 is 2, 2 degrees of freedom. So this is my asymptotic significance. Right? So this is called as the p-value. Right? So the p-value should be less than or equal to 0.05. 0.05. So that 0.05 means what actually? Right. So this is -2 plus 2. This is -1 plus 1. So this is 68%. This is 95%, and this is 99.7%. Right. So this is what actually you are. So that means what is it actually you have here? So that means here, so this value is what? That 0.101 where it is falling? In this, the 0.101 where it is falling? Where it is falling in this? Is it going here? Is it going here? No. So it is falling within this AUC, area under cover. So that means actually the male female who have registered under these three categories turns out to be the same. Not understood. No significant difference. So this is the crucial thing. If you are not understood, please tell me. This is the crucial thing. You have estimated chi-square. The chi-square value is estimated. Depending on this, you have to talk about what? Acceptance or rejection. So this is crucial. Right? So if you have not understood, then you please tell me. Yeah. Yes. Asymptotic significance. Yes. So asymptotic significance is nothing but the p-value. So for this particular value, it automatically gets the table value, and that table value is being calculated as this p-value.
So if it is less than 0.5,
less than or equal to 0.05. 0.05, we say that here we reject it. If it is greater than 0.05, this is. So we accept what? Another process. So actually, in testing, I'll just go slowly about the concept of null hypothesis. See, the literal meaning of null hypothesis is this. A definite statement regarding a different statement we made about the population. Right? What is a definite statement there? In this particular example, what is a definite statement I will make it here? There is no gender disparity with regard to registering under arts, science, and medicine. Always null is actually a positive status quo. There is no difference. Right? And then you are trying to accept or reject that particular null or alternative. So in this case, you should have a threshold for acceptance or rejection. The threshold which you take it is 5%. It is as good as saying that here, suppose if I am manufacturing 100 items, so statistically I say that here out of 100, 5 can go wrong. So if 5 can go wrong, then 5% is gone wrong, but even then I accept the law. Out of 100, 95 are correctly manufactured and it is adhering to the control limits of manufacturing aspect. Hence, I accept this particular law. Suppose, if it is not 5, suppose if it is 7. So, only 93 are adhering to the confidence limits. 7 are outgoing. So, that means that actually, will you accept the law? No, because you have a threshold of 5%. Right? So, that is what actually the concept which we are doing here. So, suppose if I say that here, if this probability value is less than or equal to 0.05, I say that there is a difference. That means the people who are registering in these three, among these male and female, has got a difference, and then they are not acceptable. It is not the same. The hypothesis is rejected if there is a difference. In this case, we are accepting that they are the same. Right? So though the difference we are seeing it in the expected count, 53 to this, 97 to this, 45 to this, 27 to this, 55 to this, and 42 to this. So this difference is not a significant difference. It's not much. That's the reason you are accepting the null hypothesis. What is the null hypothesis? The male female who are registering under art, science, and medicine seem to be same. Is my null. Status quo. Alternative is what? The male female who are registering under these streams of study differs. Right? So you are accepting null, that means you are rejecting alternative. So this is what actually you do. So we'll see the other one I have done it here. Now you just tell me all of you. So this is called as cluster bar chart. Yeah. See here. So this is the other comparison I have done. Gender versus entity status. Undergraduates, MSc postgraduates, PhD postgraduates, and others. Right? So what is the null hypothesis here? Male, female, registering under these attendee status is the same. Positive definite statement is same. Versus alternative is there is a difference. Male, female, registering under that. So I just calculated the chi-square. It is 9.457. Degrees of freedom is 3. And then the p-value is 0.024. So will you accept null hypothesis or alternative hypothesis? You accept? Because it is less than 0.04. So you accept? Reject null. Very good. So that's what actually I wanted. Less than 0.05, reject null, accept the alternative. That means, what does that mean? When you reject null, perfect. Now you have understood. That is actually I wanted to say that. Right? So there is a difference that these people, these two gender are registered under this category is different. So in the previous case it is the same. In this particular case it is different. Null is rejected, alternative is accepted. That's what actually you can understand under this particular category. I hope it is clear. Right? Okay. So this is the analysis for nominal data. I've done the only nominal data. So what else I can do with this particular file? This particular data set. Yeah. What else we can do? What else we can do with this data? What statistical analysis we can do? Huh? Mode. Mode and median is okay. No. Yeah. No for what?
How they are distributed?
So this innovation should also be there for a data scientist. See, ANOVA he said, ANOVA should have categories and you should have a dependent variable. So okay, dependent variable, I say that age is my dependent variable. Category is only 2. So 2, you don't do ANOVA, you just go for a 2 sample T. 2 independent sample T. And moreover, this is actually large sample test. I cannot do a t-test. Right? What else you can do? concentrate on continuous variable. What else you can do? One hint is you just only concentrate on this. So, what is it? How do I get it? Why clustering? See, very simple. Clustering is advanced. Clustering, what you get only clustering of how many are there in 15, how many are there in 16. So that you can get it. But you cannot do that here. Yeah, grouping means what actually you are not really doing a continuous data analysis, but you are making continuous into discrete. That you should not do. You don't want to see that here. See, this is actually a university data, student university data, right? So you have already seen faculty status and etc. And then also age. You do not see that here whether here young age people are studying here or old age people are studying here, right? And what is the median age? How many are above median age? How many are below median age? And what is the variation in their age group? So these many answers you can have to do. Yeah.
Because basic descriptive.
Basic. Descriptive statistics. That's all. But descriptive statistics will you get it? Median only you'll get it. Right? But how many are above median? How many are below median? Right. So what is their trend mean? Trend mean, etc., etc. You don't get it in this. So for this, see here, why I am so much stressing is that here you can as well do an analysis by taking continuous versus categorical. So for this, you can as well construct what is a test called what is it called? Box plot. Stem and leaf. These are two of the things. Stem and leaf are box plot. That's exactly what we do. So I take practically is this thing. So I can either do academic status and this also. All the three. So age in years is my dependent list, which is continuous. So plot is histograms. It's statistics. Yeah, box plot are done it. Right? So you just see here. Mean is among males, mean is 31.56. Right? Then median is 30. Right? So then variance is 57. So that means what does that indicate? From 31 to 57 is there age group people. So that means a lot of variation is there. So that indicates what actually? So this the data which is collected is not from a day college. It could be people who are working and then studying also. It could be a engineering college. That's sort of a conclusion you can also make it from here. Right? So that is what actually you have here. Standard deviation is 7.5. Right? So minimum age is 20, maximum age is 57. The difference between 57 and 20 is 37 range. So this is how we just read. So this is skewness. So this is definitely not a symmetric data. If it is symmetric data beta, this should be 0 and this should be 3. So here it is 0 and 3, then it is symmetric. So, but here it is 0.91 and 0.620. So definitely this is not actually a symmetric data, it is asymmetric data. Right? So therefore you have this sort of. Then females, you have this 30.39, right? So here it is 31, and this is 30.39. Then median is 29, and variance is 55. So even females who are greater than 13, there are people studying in this particular. There are students who are there in this particular sample. Okay. So this is how you got this thing here, median age, etc., etc. So this is this analysis. So this is exclusively what? This analysis is done for continuous variable. What is categorical? The categorical is male and female. So this is actually a analysis for categorical versus continuous data. So this is how you just got this particular data evaluation. Right? So these are the maximum linear estimators. So this is how you just get it. So this indicates here that there is not much male and female attendees. There is no difference in this. So all these are the various statistics which you have listed here. So this indicates that the mean constant is this much, and there is no much difference as far as the averages here. So estimators seem to be not having any much outliers. That's what actually you can study here. So these are the percentiles. 5 percentile is falling at 22 age group. Then it's 10, 23, 25. If the percentile values are 95, this we calculate. It is also no less than 25 is there. So and then no less than 90 percentile is there in this data. So these are the various values which we have calculated. So similarly, extreme values is being studied. Highest male, these are in this is the case number, this is the value. So these are all age groups. So 328 is the 57th age. So specific point out also we can also have. So in my data, 328 case, 328 subject, his age is 57. So these are the extreme guys. So the extreme guys are around 5, and lowest guys are case number 247 is 20 years age. So that is what actually here. So female also is the same. So that is what actually you can also see from this particular extreme values. So this histogram says that here this is not normal. So this is negatively skewed. Right. So this indicates. So this is also negatively skewed. See, this is what I was just talking about. This is your median age. Right? So above median, this is my variation, standard deviation. And this is the low standard deviation is, so that means age higher than 30, there are a lot of people. That's the reason the variation is quite high. So lower than 30, much variation is not there. Similar is the case for the females. So that is how you just do the analytics, and then these are the outcomes which you have. So that is what actually you can know from this particular analysis. So the same is done for attending status, same material. So this is also negative skewed for all the 3 categories. So instead of 2, you will get 3. This is also your art, science, and medicine. This is what you get. So the outliers are here, outlier in this case. So this is lot of variation is there in arts. So that means most of them have taken arts faculty, then science and medicine. Lot of variation is also there in the age groups. So that is what actually interpret from this particular thing. So this is the context in which you estimate and test. And then see that here how best we can also say that they accept or reject the null hypothesis. So any other this thing which you have got after demand. I'll just start the advanced modeling. Which one you want? I mean, I will tell everything, but which one is more popularly wanted? Discriminant analysis. And factor analysis. Factor analysis. Then cluster analysis. Yeah, those who have joined, any other doubts in this? This is the basic thing. So there are many basics, but this is the basic thing. With which you can as well do that. Any other thing? So because univariate, there are many tests. You have t-test, ANOVA. See, ANOVA, why you do ANOVA? ANOVA is nothing but you want to segregate the variances. Like for example, if I say that we have Yij equals to U plus alpha I plus beta j plus epsilon ij. So this indicates overall mean effect. This is your ith treatment effect. And this is my jth log effect. And this is my relevant. So when you have this type of this thing, you can also construct. So that also I'll show you another variance. See here, what is null hypothesis? Null hypothesis is that here alpha 1 equals to r, simply a generalized disease. Alpha equals to 0, alternative is alpha is not equal to 0. And then alpha beta j equals to 0, alternative is beta j is not equal to 0. So this is how to do an answer two-way classification. Then one-way classification is this: mu plus alpha I plus epsilon I. Only treatment effect, not block effect. So what is this block and treatment effect? I just show you. See here, if you just see this particular problem, what is this actually here? This is A is one treatment, B is another treatment, C is another, D is another. So there are four treatments out there, A, B, C, D. So this these are the weights of the chicks, right? So ration A, so that is feeding A as given, and then they have this particular weight gain is being seen, right? And then B also it is the same. If you see this independently, A, B, and C and D, if you just see here, so they are not lot of variations seem to be there. If you just see that here, D treatment, so that is D treatment means actually it is D feeding. D feeding has given very good weight, 169, 137, 169, 85, or 154. So this is what actually. So now you as a data analyst, your job is that here you want to see that here whether which feed is more effective, which feed is more effective, and which feed is not effective. That is one thing. Another thing is that here overall is it significant? That means my null hypothesis is that here feed A equal to feed B equal to feed C equal to feed D. So this gives a good weight in the chick for the farmer. Right? So that is what actually my null hypothesis. What is my alternative? A is not equal to B is not equal to C is not equal to D. Alternative is always negative. Null is always positive. Right? So I say that here it is equal. Right? If it is equal, there is no question of going for different feedings, right? You understand? Right? So now I want to see that here which pair gives me the best this thing. So for that reason, you just go for what is known as enhancer one-way classification. So that enhancer one-way classification, we just see that this is what the data. So if you just see this here, this is on A, 6 observations for 5 observations for A, 5 observations for B, 5 observations for C, and 5 observations for D. So this is what actually you have. So the treatments are named as 1, 2, 3, 4. So in this particular fashion, if I do in SPSS, you cannot do. You have to have this sort of a formatting. Right? So all the 4 rows into one column, and you notify each row as 1, 1, 1. So that is the first feeding, second feeding, third feeding, fourth feeding. So now I do the analysis. Compare means one-way ANOVA. So that is weight is by dependent test, treatments are by factors. Most of these is significant difference. There are options. Prescriptive statistics. So I got it. So this is feed A. Feed A is 5 observations. Mean is 43.8. But if you see this here, it is increasing. The average weight of the chick with this thing is increasing. Right? So if you just see the variation, the first one seems to be useless. Less variation. Right? 30. Why? This is 31, 22, 34, and 44. Lot of variation in the chick, this thing. Right? So then this is lower bound, upper bound, minimum, maximum. Right? So then ANOVA one way I have done it. So that is between groups, that is treatments. How many treatments are there? 4. 4 minus 1 is 3 degrees of freedom. And then this is the error. Error is always less. 722.425. So then this by this is the ratio, F ratio, Snedeker F. Right? So this you got it. So that is how I calculated the F. The F is calculated 722.45, then 425. And then the above one is 8744.280. So this value turns out to be 12.105. So what did I say? The null hypothesis. What did I say? Null hypothesis. A equals to B equals to C equals to D. And alternative is A is not equal to B is not equal to C. D. Right? That is what actually. So now, what is this here? If you just see the p-value, p-value is what? Reject null hypothesis. Reject null hypothesis. It is less than or equal to 0.05. 100% significant increase. So that means what actually? Reject null hypothesis means what actually? There is an effect among these 5 treatments. Right? So overall model says that here there is a difference. So you cannot compare A as equal to B, B as equal to C, C as equal to D. Right? So now what is actually I am interested in? I am interested in more on the pairs A to B. See, because this gives me that here definitely there is no difference. But which one I can draw? In the next experiment, suppose if I have some new chicks, I want to improve their weight. So all the 5 once again I have to give, not necessary. I take only those are effective, right? So I do so much of analysis to decide which one to draw, so that my profit will be more. Right? So for that reason, I do a post hoc analysis. So that post hoc analysis says that here, the post hoc analysis says that here, A to B not significant. Right? A to C, it is significant, less than 0.05. A to D is 100% significant. So that means instead of B and C, I can as well feed with A and D. So you can say that here why you have dropped C, because it is A to C is also significantly different, but it is marginal. It should be less than or equal to 0.05, so the difference is only 0.01. So instead of 95, it is 96. It is 0.04, yeah, 96. So it is borderline. So I say that here A and D are the best suited values. Sorry. So this one, this fourth, D is the best. Then also you take it D when you compare with 3 also is very good. So C and D are the best one with which you can continue the future experimentation. Right? So that critical difference also you can as well calculate. So that is what actually you can as well do under this particular context. Right? So yes.
So my question is like, why do we choose only no?
What?
We chose only a no test.
Yeah.
So what is the main case?
Yeah. What else you can do? You just tell.
Being aware of the guess.
No, see, some guess, nothing wrong in it. See, I have also started like you also.
Okay, we did chi-squares.
Yeah.
So why not chi-square?
So what is this actually? Chi-square, when do you go for? When do you go for? It is actually a scores. It's only a scores, right? Scores means what actually frequencies, right? So they are attributes. You are testing attributes. Here, are they attributes here? No. So you can as well do a descriptive statistics. That's what actually I have done.
Yeah, it's not descriptive statistics.
Yeah. So mean, median, mode, and then the upper bound, lower bound, etc., I have taken. Right. So what else you can do? You can as well, as you say that here, you can as well do a 2-sample T, independent sample. A to B, A to C, A to D. That's what actually I have done it. That multiple comparisons. So beyond that, I cannot do any other.
Can we also write like there are 2 types of tests in our body?
2A NOVA. 2A NOVA is that. That's what. So that is 2A NOVA means what actually you have a row. Now we have taken row, right? Column also. Column also. See why 2A NOVA? You have ANOVA also is there. Multivariate analysis of variance. ANOVA. So only thing is that here you have to have So when treatment effects, see it is like this. Suppose if you just collect data, Jersey cows gives more milk, right? So here breed differs, right? You want to have breed variation. So even it's a very premier breed, if the ration is given a low nutrient this thing, the effect of milk, the output will also be effective. So definitely the variation among breeds and as well as the yield are also is of interest. So then you just think about tube analysis. So here I am only interested in knowing the which treatment, that is which feed is more effective. So only feeds are being tested. Right? So but here I'm interested more in feeds rather than any other thing. So here breed is not being taken. So suppose if I just take it, the first column it represents breed 1, breed 2, breed 3, breed 4, breed 5. So then I say that we have breed variation and column variation. Yeah, any other questions like this? Then only you can understand. See, he has rightly put that. Why only you have done ANOVA? Why don't you do any other test? Can you think about any other test for this? Chi-square you cannot. Chi-square is exclusively done for discrete data. So this seems to be a nominal. It is not nominal or ordinal. It is exclusively a continuous data. So hence I have just gone for an asymptotic. Names of the test? Yeah, I told you this ANOVA is for continuous data. T-test is also for continuous data. T-test for single sample. So you want the formulas or you want to know? Names. T-test for T-test for one sample. So that is T equals to x bar minus mu by S by root n. So T, when do you go for? Whenever you want to test the means, you just go for T-test. One sample. Yeah, one sample, two sample. Then T-test for observed correlation, T-test for regression coefficient. So that you do a T-test. So this is exclusively for n sample size is less than algorithm. So if it is a large sample, so suppose if I say proportions. Suppose we have proportions. See here. So this type of data. Suppose if you just come across this type of problems. This type of problem. In a large city, 20% of the random sample of 900 school children had defective eyesight. In other large city, B, 15% of random samples of 1,600 children have the same defect. Is this difference between the two proportions significant? Obtain 95% confidence limits for the difference in the population proportions. So this is actually what sort of a test it is.
proportion.
Test of proportions, two proportions. Z equals to P1 minus P2, square root of PQ into 1 by n1 plus 1. One proportion is what actually? 20% of 900, 15% of the 1600. So n1 is 900, x2 is. So this problem we can as well report like this. See, this is actually a large sample test. Why I say large sample? Why I say large sample? The sample size is 900 and 1600. So n1 is 900, right? n2 is 1200, 1600. Okay. So P1 is 0.2, P2 is 0.15. Right? So I apply a Z test. So that is P1 minus P2 by square root of PQ into 1 by n1 plus 1 by n2. Right? So P, how do I estimate x1 by x1 plus x2 by n1 plus n2? Right? So how do I do this x1 I don't have. So what is the actually I do? P I define as x1 by n1. Right? So x1 equals to P n1. Right? So from yes. Yeah, x1 is 180. It is given there. Yeah. So it is x1 is 180 plus x2 is how much? 900 plus 16. Right. So my n1 is 240. So this is 0 to 425. 0, 2005. So this is my P. Q I can allocate 1 minus of P. So now everything you substitute here and then see that here. So this is actually a proportion. This is for large sample.
What if this sample is small? If sample is small, what kind of test?
Yeah, for what test you do?
For proportion.
Proportions, you don't have. Small sample. For single sample, you have x minus np by square root of np. This is for single proportion. If it is large population. So this equals to z. No proportion for small sample. Only for P, one P test is only is there. Okay. So this is how you do. So there are many ways of doing it. If you just see this here, this is the data. This is the data. So here these are the number of persons, and this is the interval, classic. So now we have to find out so that whether this is my mean less than. So this is actually a left tail less than 30.5. Left tail. So it is not a two tail. This is two tail. Left tail means this portion. Right tail means this portion. So that way you can as well do the problem of the proportions. That is how we do the problem. Okay, I'll just go to the advanced modules. See, actually, what is a factor analysis? And then first we talk about the data type which you do the factor analysis. So the data type you use is that here for factor analysis, you should never use a nominal data. Right? So that is nominal data means you actually 1, 2, 1, 2, 3, 1, 1, 2, 4, which doesn't have any importance of that particular values. Right? So that is one. Another thing is that here, if you have a measurement data, yes, you can as well use the factor analysis. So this factor analysis is actually a very useful when you talk about the reduction of the dimensionality. Like for example, one simple example I tell you that here, suppose if I just take a satellite picture of one particular locality, and then your objective of taking this particular satellite picture is that here you want to see that here how much of greenery is there in that particular locality or in this particular case. So that means I am searching for a green crown sort of a thing in the pictures, right? So but the danger is in this particular case that here a green top with a building also looks like a green figure. A green color, so hence, so a building can be taken as a green. So whenever you have this type of data, so you have a huge picture, and that picture has to be decoded into the digitized form of this particular picture. So as some of you know that here you must have studied image processing. So this particular data is being converted by MATLAB into a particular data matrix. Okay. So this data matrix is never symmetric. Right? It will be a very huge matrix. So it could be a 1,000 rows by some 10,000 columns. Right. So my objective is that here to meet that here that how many are what is the count of these trees which I want to do this. So then handling this type of a huge matrix is really very difficult. So instead I want to reduce the dimensionality. Like so this reduction of dimensionality you have already seen it in your day-to-day life, and that is one such this thing is that here we are allowed to put only a 10 MB file to our mail. So beyond 10 MB you cannot attach. So what is actually you are doing is you are zipping it and reducing the dimensionality of the file into a smaller size and then attaching it. So that also you have certain rules with which you can as well reduce only. So I cannot take this particular picture and I want to zip it. It may be beyond 10 MB. So hence I cannot connect it. So whenever you talk about this type of situation, you just go for what is known actually. I want to reduce the whole dimensionality of this particular data set into few constructs. And these few constructs should be showing up all my data which I have already collected. Right? So for that particular purpose, you just go for what is known as the factor analysis. So image reconstruction, image compression, right? Image identification, image edging, right? And then the problems which I told you, the other problems also you can as well do there. And then even in most of the NLP, NLP problems also, you can as well do the factor analysis. And this plays a very crucial role, which so it reduces the whole dimensionality of the data without losing any information of the originality. The properties of the original data will be lying with the same reduction form of the data which you obtain from a particular technique. And that particular technique is known as the factor analysis. And this factor analysis is called as a data reduction technique designed to represent a wide range of attributes on a smaller number of dimensions, right? Without losing any information. Right? So that is the main purpose of this. So you might say that suppose if I have I just collected data on a pollution, air pollution or water pollution. So air pollution has got what actually there are many things. I want to see that we are in a particular locality, how many of the companies have more than 100 employees. So when more than 100 employees are there in a particular company, the production is high, so it will be more polluted. Right? So then sulfur dioxide is how much it is there. So in these things here, suppose if I just take it 40, 50 cities, data on these variables, so then I want to see that which city is more polluted and which city is not polluted. So this type of this thing are hard water analysis, hydrology. So there the pH content, etc., etc. You want to see that here. So which one is more common in various samples which you have taken? So for that reason, you study this thing here. So for example, this is a simple example. All of us can understand that suppose that a bank asks a large number of questions about a given branch. Consider how the following characteristics might be more parsimoniously represented by just a few constructed factors, and that is this: friendliness of staff, time spent in lineup, assistance via telephone. These three are the attributes. So which the factor analysis, if I just collect data on this, it reduces to a service factor. I'm not dropping anything. All the three represent service. And similarly, distance of bank from home, hours of operation, availability of parking, proximity to other stores where you frequently shop, turns out to be a convenience. Right? I'm not dropping anything. Reduction means people think that here we are dropping the attributes. No. I am representing all them into one particular reduction. So that is my eigenvalue, that is my convenience. Right? Then monthly account fee, charge for withdrawals and deposits, loan interest rate is my cost. So all these 3 plus 3, 6 plus 4, 10 variables have been recasted into 3 factors, and these 3 factors is enough to represent these 10 attributes. So that is what actually is the factor analysis. Okay. So we'll see. So benefits include a more concise representation of the marketing situation, and hence communication may be enhanced. Fewer questions may be required on future surveys, and perceptual maps become visible. Ideally, interval data. What is interval data? Likert scale. Strongly agree to strongly disagree. Or 10-point Likert scale. You buy a bike, you will immediately call the next day. How is our customer? Are you satisfied? How are various questions you put? And then he'll ask you to rate it between 0 to 10. 0 being least, 10 being the highest. So that type of data is the most suited for factor analysis. So one such example I have taken up, and then this is what actually you have. So this is also on a 0 to 10 scale. Very untrue is the least, very true is the highest. So that is given a 0 ranking, and this is given as a 10 ranking. So this is these are the attributes asked the customer. They are posed to the customers by the seller of these brands, 5 brands, that is B2, Honda, Lotus, B1, So there is appeals to other people, attractive looking, expensive looking, exciting, very reliable, trend setting, has the latest features, luxurious, distinctive looking, being you can trust, conservative looking, family made, and basic transportation. So what is the purpose here? Why he has taken this? Any idea? Any guess? Any good guess? So you might say that you want to consider all the factors. Yeah, what is the objective of the dealer? So I'm selling these 5 brands. What is my objective from these customers? Yes. Which is most accepted by you. So only you said brand you are talking about brand, but brand is not the thing. So see here, as per your question, I said retail. I will say that here appeals to others people I buy. So I will say that here this is most important for me. I'm not satisfied about myself, but I'm more satisfied about my friends saying that here it is very good. Right? So that sort of a thing. So amount, see now, remember, if I do, this questionnaire is being given to all this thing, I get 100 into, suppose if I say that there are 50 people are here, 50 into 13 variables are there. 15 into 30 answers I get it. Right? So, what is that actually? So here this is appeal to others people, attractive looking, expensive looking, exciting, very reliable, trend setting, has the latest features, luxurious, distinctive looking, name you can trust, conservative looking, family vehicle, and basic transportation. So he wants to, he has elaborated his study. But what is that actually the factor analysis gives you? As per the previous example.
So many concise some of these
Only one?
no, one or two, some of who are with them, like if you saw the attractivity, you see a similar.
Similar means what actually? Can I rename it?
Yeah.
Look
of aesthetics.
Aesthetics. So you think aesthetics is the most, aesthetic is not for a car, right? So this is most important. This is most, yeah?
Next dimension.
Which one?
Dimensions.
Yeah, you have to reduce them into lesser dimensions, correct? But what are those lesser dimensions? Can you see, foresee? See, because this is reality. You are given this question. You as a data analyst, you have already decided to do a factor analysis. What is it actually I am going to get it, how it looks? I mean, you know everything, but you are not answering it.
On the price.
Yeah, only price.
Price and lead.
This is what it is. See, all the customers see the reliability. How reliable the car is. Right? So that particular factor and the other factors, if anything are coming in, I want to take it off. Right? So I do the analysis. Okay, so this is fed on to a SPSS sheet of this. So these are the various data points, 0 to 10 it is taken into consideration. Right? So now I just get the output. The total variance explained is how much? Just here, this is around 70%. Right? And they are only 3 components. And these 3 components are this. Right? So you might ask why you have dropped. Why you have stopped at 3 only? Why not this thing? So I just considered only the rotated component matrix, which is 3 only. Why? Because I see for an eigenvalue which is greater than 1. So here it is greater than 1. So 70% of the coverage is being taken. So the dimensionality is around 70% for all the 13 variables. After that, you just see that there is no much difference. These values, percentage of variance, they are almost 1. The first one is 44%. The second one is 15%, the third one is 9%, then 6%, right? And then also after this, the total cumulative percentage of coverage of the whole data seem to be around 70%, for which the eigenvalue is 1, greater than 1. So I'm just seeing that. So that's what actually I said. Cumulative percent of variance explained is around 70%, and I'm looking for a eigenvalue as 1.259. So hence, the whole data represents only 3 components. Right? So now I study those 3 components. Right? So those 3 components are this rotated component matrix. See here, nothing is dropped. All the 30 variables are taken. Don't think that your reduction in dimensionality means what actually the variables are being dropped. No. Right? So you have all the 13 taken into consideration, and then this is component 1. This is component 2, this is component 1. So now I have to select it. I have to select it to do the further analysis. Okay. So I do that. So I just take it this. Appeal is 88%. Attractiveness is 77%. So I've chosen the highest one. Highest positive and highest negative. This is highest negative. These three. You count all the right rectangles, there will be 13. Nothing is dropped. In the first component, 1, 2, 3, 4, 5, 6, 7. 7 factors are there. In the second component, only 3 are there. And in the third component, another 3 are there. 7 plus 3 plus 3 is 13. All the 13 are there. So now I further do the analysis for this. So I just take it. These 7 is taken as expensive, exciting, luxury, distinctive, not conservative, not family, not this. So I have taken these. The next one is appeals to others, attractive looking, and trend setting, reliable, latest features, and trust. So now I have to name them. So what shall these components be called? So these components are taken as these are the exclusive characteristics. If I just see my customers are seeing for exclusive characteristics, so these are the factors that are important. If it is a trendy, so youngsters are coming in and taking a car, so then they see appeal to others, attractive looking, and trend setting. If reliability, all old days, they take it reliable, latest features, and trust. So this is the distinction that is being done by the factor analysis, by the reduction of dimension. So these are the 3. So now among these 3 also, so this confusion I cannot have. So among all these 3, what is the ultimate answer? Can I answer? For that, I just calculate the component scores. So that is exclusive component score is expensive, exciting, luxury, distinctive, minus conservative, minus family, minus basic divided by 7. So I am calculating the averages. Right? So why minus is because these are minus. So these are minus. All the 3 are minus. So minus. Then trending. Then reliable. So I just calculate that. It is there, complete variable. So I just calculate that by this thing. So for each car, I have calculated this. P2, number, voters, minimum, so this is what we just got these things evaluated. So now I just collated all the results which I got it in the previous slide, and then I found that here whether you take a sporty car or any other car, but all the customers who visit me is the reliability aspect. So this is the most important aspect with which I can actually get the things done. So in this particular case, reliability aspect is being mostly sought after by the customers who visit to select any one of these 5 values. So that is what actually the answer for this particular problem. Suppose if you just take it any other distance, I said that here I want to do a analysis for pollution analysis. So what are the factors which are influencing the pollution in these cities? That can also be studied. So that is exclusive. The data is not with the ordinal scaling, but it is with the what? It is with the, what sort of a data? It is data with measurement data. So that is what you do under the factor analysis. So this is how you talk about the factor. Any doubts here? So I was just talking about. I want to duplicate you have data of this nature. So that is, you have x1 is one variable, x2 is another variable, x3, x4, x5. Right? And then there are so many groups are there. So how many groups are there? So 1, 1, 1, 1 means actually it is 6 observations belonging to one group. Right? Two groups. There are two groups are there. So what is the distinction of this? So x1, this is actually archaeological data. So x1 is what actually? x1 is actually greatest length of skull. And x2 is actually greatest horizontal breadth of the skull. Then x3 is height of the skull. x4 is upper face height. x5 is face breadth between outermost points of cheekbones. And then there are two groups, group A and group B. Right? So when I say group A and group B, what does that mean? So that this indicates that here, see, I assume that group A is this is group A, then this is group B, right? So this is the area. There is a overlap. This is my overlap of these two groups, right? So now, if I say that here group A and group B are the two groups, if I discriminate these two groups and then say that here what is the misclassification? What is the misclassification probability? I get it from this, and then that means that actually there are certain skulls which are actually group A, they are classified, the archaeological department people. But these group A could be a mixture of group B also. Similarly, in group B also, there is some sort of a group A cases also are fallen. So now you have to discriminate these two groups and do the correct classification. So what I am saying is this. So suppose if I say group A and group B, right? And then this is group A and this is group B. Right? So I know that this is group A. So group A, this is my correct classification, right? And group A to group B, this is my wrong classification. Group B to group A, this is also my wrong classification. Group B to group B, this is my correct classification. So this I want to do it for this particular data in such a way that here, how many of these 30 to 16 plus 17, I think there are something, right? So out of these 35 skulls, how many are really belonging to group A and how many are belonging to group B, right? So there is some sort of a misclassification. What is the misclassification percentage? And what is the correct classification percentage? So that is what actually I want to know that. So you might be wondering that here, what is so great in why do you want to discriminate this and then get the wrong classification? Right? So what is actually the story of this particular data is that here in a particular location, they have found this many skulls. And then they found after a scientific evaluation, they found that here there are two groups. And then the archaeological people thought that here there could be a war there. Right? So now this data has been given to a statistician to see that here whether really there are two groups, really a war has been taken place, or a calamity where the misclassification rate is very less. So that means actually they have died due to some calamity in that particular district. So for that type of a situation, you want to study this data. Right? So for that reason, you just go for what is known as the discriminant analysis. Let's just go to the presentation. So, so this is what actually I told you earlier. This is used to predict group membership through a set of continuous predict tasks. So this could be a multivariate analysis of variance. In reverse ANOVA, we ask the groups are significantly different. So in what way this will be ANOVA? In what way this will be ANOVA? Why I call it as ANOVA? There are 32 skulls, right? And each skull has got 6 observations. 6 observations. That is 6 measurements. So the first skull, is it significantly different from second skull? What did I say? ANOVA. ANOVA is A equal to B equal to C equals to D. So here, skull 1 to skull 32. It is the same. That is my null hypothesis. Versus the different. So that's the reason I said that here it is actually a ANOVA. Why it is multivariate ANOVA? Because each skull has got 6 measurements. And like that, there are 32 skulls out there. So I just calculate the overall and skull 1 to skull 2, skull 1 to multiple comparisons. Post-hoc analysis. I can as well do that. So that is what actually you derive from this particular context of the same. So we determine how can continuous variables be linearly combined to best classify a subject into a group. So that is nothing but what actually it is actually a linear combination. What is linear combination? The model which you have here is actually so I am estimating this. This is my data points. 6 data points. So this is my group. Right? So this is actually a linear combination. x1, x2, x6. So my mathematical model turns out to be a1 x1 plus a2 x2 plus and so on and so forth a and xn. Right? So this is my dependent variable, which is q. So I am discriminating. So there are 2 groups. And then, so this is my data, I am estimating these values, A1, A2, A2. So that is what actually I just do, that linear combination of this. So that's what actually I said earlier, 2 populations, phi 1 and phi 2. So that is one set of group A, another set of group 2. So we have measurements x1, x2, xp. So in this example, x1, x2, x6. So on each of the individual concern, given a new value of x. So suppose if I just take, if I get another skull with these 6 measurements, so whether now I have to classify whether the new measurements, whether it is belonging to group A or group B, can be done, and that is being classified once I just calculate the discriminant analysis. So this would be like this. That's what actually I'm just talking about. This thing. So this is one group, this is another group. So this is your misclassification. 1 as 2 and 2 as 1. So this is the misclassification which you want to get it from this particular problem. So this is the theoretical aspects. So that is, you want to say that here whether this is significant, whether misclassification probability is how much. So that is being evaluated by the condition. So ultimately, this is what it will do under this particular case. So these are correct classifications, these two are the wrong classifications. So cost also you can also do. So I'll just go for the analysis of this. Because reduce. So reduce is how can you reduce? It is actually you have to put some cost and then reduce it. But here, in this particular case, there is no question of any reduction. See the example which I am going to see. So what is that actually? Suppose if it is actually discrimination between some costs, then the reduction in cost will come. See, the cost is dependent on the determinant. You cannot reduce the cost. You can assign the cost. If I assign the cost of misclassification is high, then definitely the profits go down. So you can assign the cost, but you cannot reduce the cost. You have measurements. All means what actually you can have infinite number of observations on each one case. Suppose if you have taken all your clinical parameters, so that runs to some 100. I just take it. He has got another 100. So now I want to have some commonness among you, and also some uncommonness. So this actually is done in most of the DNA. Say you compare a controlled DNA with a diseased DNA. So in what way the diseased DNA is different from the controlled? Similarly, protein matching. Similarly, RNA matching. So here, what actually happens here? So the data is DNA is not actually numeric. It's ACTGA. ACTGA is actually an alphabet. ACTGA is alphabet. So that you convert that into a digitization and then do the DNA analysis. So you can take it any number. Ultimate goal is again what is the correct classification. What is the percentage of correct classification? Suppose if the correct classification is wrong, then that means actually there is definitely some erroneous aspect is going on within these two groups. So the correct classification is less, but the misclassification is high. So that means the discrimination between these two groups is also very well. The correct classification is high, and then misclassification is less. So then discrimination is there. So they are comparable groups. See, ultimately, what is the next case? If error is high, means what actually they are not comparable. They become independent. That's all. So I do this analysis. I do this book analyze. Classify. Discriminant. This. So all the 6 measurements are good. See, I have done the distributed analysis, and then I got this thing. So these are the descriptive statistics. So from here, so these are all the 6 variables. Mean standard deviation is being calculated. So the second group also mean standard deviations are also calculated. Okay. So here you just see the mean of the first group and mean of the second group is different. 175 and 185. Then the greatest horizontal breadth is 139 and 138. So there is no difference here. So there is comparison can be done here. Then if you just say this is 131 and 134. So then 69 and this is 76. This is 130 and 137. Slight difference. So if you just see this here, so if you just see this here, the variation, this last variable like 6, this is 8.13, this is 4.03. A lot of variation is there. So this is also just here. This is 6 and this is 8. This is 7 and 6. So 6 and 7. This is 3 and 4. So this is not much, but this is almost 50% differences. So with this, what is actually you can understand? You can understand definitely there is some sort of a misclassification can be seen in this data. Right? So that we have to establish. So I said univariate ANOVA. So I said that here case 1 of the first group. Right? So greatest length of the skull. So for all the 32, it is being calculated. So that is there are two groups. For all the 2 minus 1 is 1 degrees of freedom. 30 observations here, highly significant. So that means all the 32 measurement 1, all the 6 measurements in all the 32 is 100% significant. The greater and horizontal skull seem to be the same. You getting the point? What I am talking is this. See these 6 measurements of the first group, right? And then these 6 measurements of the second group, right? I just done an ANOVA for this or 2 sample t test, and then similarly for all 17 here and then all 15 here, and then compare them and then found the following results. So that's what actually test of equality of group means. The first 6 measurements of the first group and the second group's first 6 measurements, they are different significant, 100% significant. P value is less than or equal to 0.05. This one is greater, it is not significant. Second measurement. First group, second 6 values. Then third is also not. Fourth and fifth are significantly different. Right? So the first one, fourth one and fifth one, they are significantly different. So with this, you can expect that here there is some sort of a inequality among these groups. Okay? So this group statistics is being calculated. So this is case wise. Case wise is what actually actual group is 1. Actual group is 1, but the predicted group is 1. So correctly classified. Okay? So it is correctly classified and there is no significant difference. Actual group is 1, second measurement, third, fourth, fifth one is there is a misclassification. Actually, it is actual group is belonging to 1, but it is misclassified as 2. Right? So one misclassification like this. This is also right. So out of 17, 3 are misclassified. Right. So then I can as well see for the second group. For the second group, 3 are there. So this, and this, right? So now I just go for the misclassification table. As per this is case-wise inserts. So this is how the data is doing here. See here, this is the case summary classification inserts. 1 has 14 cases. 1 has 2, 3 cases. Its percentage is around 17.6. This classification. Correct classification is 82.4. Out of 14 out of 17 is correctly classified. 3 out of 17 is wrong classification. The percentage is 70.6. Then second 2 to 1 is around 20. 2 to 1 is 3, their percentage is 20%. 2 to 2 is 12, the percentage is 80. So overall percentage is 81.2%. So it's a correct classification is of original group cases correctly classified. So it's a very good classification. So it discriminated properly. So definitely whatever actually it indicates here, it indicates that here it is definitely whatever the archaeological department thought about it, the data has got two groups. So definitely it is not actually a calamity, but it will be a war would have been taken place. So that's the reason you have got two different types of skulls from this particular location. So that is what actually you can as well. So the same thing you can as well do for brand equity, right? Cost of the same product, right? Production. You have two machines, and then the production for 8 hours is there. So is there any the number of items produced in one machine and it is different from the number of items produced in the second item. So though they are the same something normally distributed both the machines. So that type of a situation you can as well study under this context of discriminating and doing it. So here actually two groups only. You can also go for multiple groups. So then if it is a multiple groups in this called as multiple discriminant analysis, LDA. So this is actually a linear discriminant analysis, LDA. Multiple groups if you have multiple discriminant analysis. So that can be also regarded. So only thing is here. So when I say multiple groups, so then you have a number of normals. So this many normals will be there. You have to evaluate that. So in a binary two group case, it is simple. So this is how we do that. So if you have multiple data, multiple variables, then you can also evaluate the LDA. Used to test the homogeneity of several variables. So that's what actually you see that here. Suppose if I have a number of variables, this will be. Okay, so that's what actually you have here. Like for example, we just see this here. You have different types of acts. Right? So you can as well classify these acts into color-wise distinction can be done, or the shape of the act also you can as well do that here. So this is actually used first used by Dyrand in 1959, and then it encompasses a number of different algorithms and methods for grouping objects of similar kind into respective categories. So arranging objects into groups is a natural and necessary skill that we all are shared. For example, this. So if you just consider this, so you can also classify these hats as per the size of the caps and color of the caps, right? So are designed as per that. So a more precise this thing is this. Right? So there are 12 phases in this. So in what way they are this thing? How do you place them? So by placing the following phases into groups, what criteria do you apply? Size, act, glasses, gender, hair color. Is there a different classification that makes much sense? So as per this, you can as well do that, and that is being done through the context of what actually by seeing it. See, if you see here, some faces are laughing. So this is actually a doubt whether he's laughing or his face itself is like that. So that we just do that. That's what I'm saying. So phase one is gender. First phase is male, female, male, right? So male, female, male, 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 like that. We have done it here. So then if he is wearing glasses, is well. So that guy is not wearing glasses, that lady. So that is how you have the mustache. So when you see this here, so this formulates all these M's becomes into one cluster, and then these F's becomes into one cluster. How is this possible? So in this particular case, you take them into one cluster, and you all F's into one cluster, all M's into one cluster. That is not possible. In a data science approach or a big data analytics approach, it is not possible. So to have this type of a situation, what normally done is that here they take the distance between two samples. What distance? Equilibrium distance. Or if it is a multivariate case, you just go for a Malan distance. Right? So that's exactly what we want to study. Right? So this is how we. Cluster analysis is actually an exploratory data analysis technique. And then this is designed to reveal groups of by distance close together observations should be the same group. So they should be by distance. That's what actually. What distance? Euclidean distance. Be in the same group, and observations in the groups should be far apart. So applications are plants and animals into ecological groups, companies for product usage. Say like for example, you say that we are refrigerators. Right? So each refrigerator has got its own functionalities. So suppose if you just go to a showroom, electronic showroom, Bajaj Electronics, if you just go, so you can see a LG, you can see a Samsung, you can see another model, IFB, etc., etc. But you want to have maximum functionalities on a particular fridge, and at the same time, the cost should be less. So how do I study this sort of a market approach? So LG and Samsung, are they same in their functionalities? Same these things are there. So if you just talk about TV also, so which one is more facilities? So that facilities are interested. So then how do I know that? So unless I note down all the functionalities and then make them into a cluster analysis. So some falls into all the same functions will come into one cluster, which are not there, it goes into other. So definitely within this particular cluster they are homogeneous, but between these two clusters they are heterogeneous. So that sort of a clustering we are interested in. So heterogeneity is one cluster, they are heterogeneous, they are different in these two. So a customer wants what are heterogeneous. So how many functions are same in this? What more are there in another group? So I'm interested in more in that than the same set of systems. So that type of a situation is possible to the case of cluster analysis. So there are two types of methods: hierarchical, so it requires observations to remain together once they have joined in a cluster. Complete linkage between groups, average linkage, and voids method. Non-hierarchical, no such requirement. Research must pick up a number of clusters to one. That is K-means algorithm. So normally we use the second one. K-means algorithm only people will do in a clustering problem. So it is like this. If you have data on alcoholics, right? When I say alcoholic, day and night he will drink. Right? So suppose if I just take data on this type of data, right? Some people drink for social drinking. Right? Some people will drink for any success or any distinct. Yes, I have that slide also. So there are different types of people. So now I don't get the different types of data individually. So I get a mixed data of this type. So I want to see that here, I want to map this data into similarities. And then how many groups are being made out of this particular data. So whenever you have this type of data, so then I just go for what is known as clustering. So that means that actually among the set of variables which I collect data, I want to see that here how many of them are homogeneous within themselves and how many are heterogeneous. All homogeneous fall into one cluster, all heterogeneous fall into another cluster. Right? So that type of this thing is being done under this. So relatively small samples use hierarchical, less than a few hundred. The large samples use k-means. So that's what actually I told. Whenever you are dealing with the big data situations, you just go for k-means. Suppose if it is a data science problem, you know the difference between data science and big data. The difference is this: big data is actually it gets with 4 weeks, while data science is not 4 weeks, but it is a small sample. So whenever you have a small sample and you want to run a sampling aspect, then you just go for the first one, small samples. Suppose if you have a large sample, then you just go for the k-means. So it is a bigger data. So that is cluster analysis is a class of statistical techniques that can be applied for data that exhibits natural rules. Cluster analysis sorts through the raw data and groups them into clusters. That's what it's called. The cluster is a group of relatively homogeneous spaces or observations. Objects in a cluster are similar to each other. They are also similar to objects outside the cluster, particularly objects in the cluster. So that is how you do the cluster analysis. So we'll just talk about this. See here, some people will drink for social appeal, some for status, some individual. These are alcoholics, and this is for continence. Right? So these are the 4 groups. If you say, so I collected data on this type of a situation. Suppose if you just take it. So there are social appeal. For social appeal, people drink. They are a large chunk. Then continence is not much here. So then for status, they are more, but alcoholics are individual are alcoholics, so they are very less as compared to this. So this is called as actually this mapping of the original raw scores. So how they become into one particular cluster. So what it does is again it calculates for each sample, it calculates the distance. What is distance? I'll just tell you. The distance is this. So this is the distance. So A is one part. Yes. Suppose if I say that this is my A in a triangle aspect, A square plus B square plus C square is my distance, Euclidean distance. So for each sample, it calculates A takes as one A square value and then B square and C square. Then it puts square root of that will be the distance. If this distance for one sample is 3.5, and if suppose if the distance for another sample is also 3.75 or 3.85, so then they formulate into one particular cluster. Right? Suppose if it is 7.5, it goes into another cluster. So that is how the distance factor is being taken into consideration, and then it formulates into one particular case of it is homogeneous cluster and heterogeneous cluster. So this is actually many distances are there. Minkowski distance. Then you have a multidimensional space. D equals to 1, it simplifies the unidimensional space. So these are the mathematical aspects here. So this is for multivariate data. You know that we have P.C. Marmabe is the Indian. He is the inventor of this Marmabe's distance, which is used for multivariate data. And this is found out by 1936. So it differs from equilibrium distance. In that takes into account of this. So here, this is the multivariate aspect. This is your variance covariance matrix. So this is variance covariance matrix. The variance covariance matrix is actually like this. So these are variance of x1, then covariance of x1, x2, covariance of x1, x3, like that. So this is variance of x2, covariance of x2, x3, like that. So this is actually a matrix. So that is the sigma matrix. What is covariance? What is covariance? What is covariance? See, variance you just calculate as one actually 1 by n sum x1 square minus x1 bar x1. Right? So the covariance of x1 x2. So this is actually a bivariate. So this will be 1 by n sum x1 x2 minus x1 bar x1 bar. So you need not worry about it. This is the formula. This is how it calculates. So suppose if I say x1 x2. This is 2, 3, 1, 4, 6, 2. This is the data I have. Variance is what actually, so this is 5, 6. 6 by 3 is 2. So this is my x1 bar. Right? This is 12. 12 by 3 is 4. This is my x2 bar. Right? So what is it actually I want? x1 and x2. Right? x1, x2. 8, 18, 2. This is 28. 28 by 3. Sorry, this is not this. Right? So what is this here? 1 by 3, 28 minus 2 into 4. Right? This is how you just calculate. So this is 1 point. So this is my covariance. So my variance I will determine like 1 by n sum x1 square minus x bar x1 square. So x square x1 square x square 4 and 1. This is 14. So this is 14 by 3 minus x1 is 4. So this is 14 minus 12. So this is 2 by 3. What is variance? So suppose if I want standard deviation, it is square root of 2 by 2. So this is what actually, this is my standard deviation. So this is how you just calculate the covariance. So now coming to that particular sigma, what is sigma? Sigma is variance of x1. So this is this one. Then covariance of x1 x2. Then variance of x2. So this is symmetry. So this is always the diagonals are variances. The upper diagonals are covariances. So in a multivariate data, you have a dispersion matrix of this nature, and then for that you have to do this here. Mu is what actually mu is your mean. So in a multivariate data, mu won't be single value as you have seen it. It will be a vector because x1 is one mean, x2 is another mean, x3 is another mean, x4 is another mean. So it's a vector. So here mu is a vector here. X is also actually your random variable. Right? So this is transpose. Right? This is your variance covariance matrix or dispersion matrix. So you have to take the inverse of this. Multiply this square root, then you get a d square. So for this what you call it, multivariate data, you just go for what is known as the value is d square. So this is how you just calculate for vectors also return. So ultimately you just construct a dendrogram. So this dendrogram is actually this is how we just calculate. So we just do a problem on cluster analysis. So if you see this, this is actually a air pollution data which I am just talking about. So the first column indicates the cities. There are 40 cities. And then they have calculated data and measurement data. This is so surface content of air in micrograms per cubic meter. Average annual temperature in Calgary. Number of manufacturing enterprises employing 20 or more labors. Population size in 1970 census in thousands. Average wind speed in miles per hour. Average annual precipitation inches. Average number of days per year with precipitation. It is much more than I've just calculated. This is not necessary. So whether why we calculate such curve? Huh? What's happens?
See how
You are normalizing it by taking 0 mean and 1 as a standard deviation. Right? That is how we do that. So therefore, so I do the clustering here. So if this nice classify. So I say hierarchical because it's a small sample. So I take all these variables. Plots, interval, square equilibrium. So that's done. So these are the equivalent schedules. So the distances, portions of distances that we have here for all the values, all the 40 cities. This is the histograms. I don't mention C. Yeah. So what is this? This is the dendrogram. Right? So what does this indicate? City 17 and city 11 are formulating into one particular cluster. So they are polluting in a similar fashion. Right? So then city 18 and city 29 is one particular cluster. City 18 and 35 is also cluster. Suppose if you just take it all these things, so 27 and above that are into one particular cluster. So the pollution levels, air pollution levels in these particular cities has formulated into one cluster, the other cluster, the other cluster, and the other one is into the other cluster. So this is what actually the clustering is being done. So the same thing I just stated. This is actually a clear-cut case of profit is dependent on the three advertisements, advertisement 1, 2, and 3. So the very purpose of this multiplication is this. The multiplication equation looks like this. So the data is there in this. So these are all what actually independent variables. IPs, and this is my dependent variable. So the data type which you should do is here. Both should be quantitative. Why should be quantitative? X1, X2, Xn should also be quantitative. Then only you can also run the regression. Right? So you have this here. So this whatever actually you calculate R square. So this is called as quotient of determination. And it lies between no negative. So it will be always lying between 0 and 1. So now I just run this multiplication. So I take it profit as given. These are independent. I've done it here. So this is your correlation, profit versus advertisement is 0.865. Right? So I've done the significance here. So this is 100% significant. P value is less than 2.05. This is 0.395. This is not significant. So Y and advertisement 2 doesn't have any good relationship. So the profit is not from advertisement 2. That's what actually I can have. Then advertisement 3 also it is not good. So as per this correlation, I can see that your profit is more with the advertisement part. Right? So that is how I just got the interpretation done for this problem. So then I just calculated the R square, right? So the Y's influence profit on these three advertisements seem to be 97%. Profit on these three advertisements is around 97%. Now, whether this is, I said I have estimated R square, now I have to test it. That is being done by ANOVA 1A, that is regression sum of squares, it is 100% significant. That means the fit is good. It's a linear fit and then the fit is very good. If it is very bad, then this would have been not significant. Okay. So then I also test that these advertisements 1, 2, and 3 are they significant or not. Right? That I just see that here by taking this the case of 1. So I just say beta naught, this is my intercept 1, 2, and 3, and then I have done a t-test for this. All the 3 are significant. So that means the profit is dependent on all the 3 advertisements. So that's what actually you can have a conclusion of the approach. Suppose if it is, if one of the variable is not significant, you can also drop it next time. And only profit is being represented by only 2 advertisements. So that is what actually we do from this.
Why do we pay attention about the significance of the coefficient in the set?
No, it doesn't have any variable to it doesn't have a variable to play a role. Yeah, it is actually by intercept. By the dependent variable is being having an intercept.
We don't
No.
no.
There is no role at all. See, if suppose if it is attached to a variable, then I am interested. Ultimate goal is that here, which independent is influencing by, not the intercept. It's a constant and it doesn't have any role to play there. It is only used to have an intercept between y on many independent variables. See, what I am saying is, see here, this is, for instance, this is constant, A naught. A naught, that is the constant. This is not significant. Whether it is significant or not significant, that's what actually he is asking. Why you are not taking it on that? So, because it doesn't have any variable attached to that particular constant. Right? So, it doesn't have any sense to have any relationship with one. But these variables, see, suppose if I say that this is one flexi advertisement, another is radio advertisement, another is TV advertisement. So all the 3 is influencing the profit variable. Right? So in this particular data set, it is influencing, the profit is being influenced by these 3 advertisements. But there would be a chance that here, the third or second or first may not influence Y. So then definitely this value will be greater than 0.0. So then you need not consider for the future course of actions. You can either drop it. So suppose if this is not there, I say only these 2 I do and my profit will be maintained. So ultimately that is actually the prediction. Regression is a prediction technique to see that here whether it is actually effective or not. Yeah, dependent. And here both dependent and independent should be quantitative. So what I am saying is, if this is qualitative, if there is 1 to 1 to 1 to data, and this is weights and heights and repeats, you should not do a multiple regression. If both should be quantitative as we have seen, profit in rupees, advertisement cost is also in rupees. So now I am just doing it a multiple regression. Suppose if it is, say that we have coronary heart disease, I ask yes or no. So yes means what actually is affected with CHD. No means he is not affected. 1 to 1 to 1 to. And then I also ask for age. So here in this particular thing, I want to estimate which age group is more prone to CHD. Right? So for this, regression should not be done. You have to go for a logistic regression. So because it is qualitative versus quantitative. Qualitative is 1 to 1 to 1 to. Quantitative is your age. Similarly, lung cancer. Yes, no, yes, no. Then what is age? So that is logistic regression. Logistic regression is a non-linear regression. Yeah, if you have any questions, I can answer other advanced models. There are many other neural networks there. For prediction purposes, you do this mostly regression. And then you have stepwise regression, you have backward regression, you have forward regression, you have reverse regression. So here, error is normal. In reverse regression, error is not normal. So those are things which they are little advanced, but if you know for a data scientist, clustering, discriminant, factor, and correlation. If you know all these four advanced models, you are done. Most often the data will be in this particular fashion. In some cases, you have to tackle with nonlinear regression. Nonlinear regression is a little tough. Scientists. So this is available in this thing is a 500 rupees. So Peter Bruce and Andrew Bruce. Practical statistics. For data scientists. This is pretty cheap. It's 500 or so or 600, not beyond. This book is Andrew D.R. Wheeler. Peter Bruce and Andrew Bruce. So, and the other one is Categorical. Statistical methods for Categorical. So these two books you can see that notes. But this just by reading or by studying you don't get it. But you have to practice. You download one particular package and start doing it, you will definitely get it. So you should have many data sets which you can download from Google Files. Suppose if you are dealing with financial data analysis, you can download from Google Financials. Suppose if you want any data on inputs and you can as well download by CSO, NSO data. But then you practice is the most essential aspect. SPSS is pretty easy to people. Freeware is not there. You can, if you want SPSS type, you have one this thing. The TSP, that is freeware. So it is the same format. Yeah, next is clustering.
Tomorrow we have a class at morning 10:30. Parties are in the child class. It's machine learning and algorithms. Okay, and after that we continue we have to present. Any doubts? While I not begin, I'll share the final presentations with Sharon. Thank you everyone.